Welcome back to asymptotics and perturbation methods. So today I'd like to introduce the topic of asymptotic expansion of integrals. It's something we talked about a little bit in the first lecture, but we're going to get more systematic and focus on this now for, I don't know, it might take us say 2 weeks or, like on the order of 4 lectures. So today's method will be integration by parts. Then we'll learn some more sophisticated things, Laplace's method, the method of stationary phase, method of steepest descent, which uses some complex analysis, and a related concept to that called saddle points and saddle point integration, which is a shortcut for the method of steepest descent. So let's just dive in. All right, here we go. All right, so you can find all this material in chapter 6 of Bender and Orszag. And there is this natural question, given that we're going to be spending so much time on integrals now for a while, why? Why do we care about integrals? And there are a lot of reasons, I'm sure you can think of many, but I would emphasize these two in particular, that many different special functions can be viewed as, you can write them in an integral form, that is, they have integral representations. So for instance, if we were doing a course in partial differential equations and studying, say, the wave equation on a circular drum head, or the diffusion of a chemical in a petri dish, any problem that has circular or cylindrical symmetry, if you're studying the eigenfunctions of the Laplacian, as would arise when you're studying these problems I mentioned, like diffusion or wave propagation in some system with cylindrical or circular symmetry, you're going to run into Bessel functions. So the most famous is this J0 Bessel function, which has a very nice integral representation in terms of cosine of a strange-looking argument, x sine of t dt. So we'll see later in the course how we can derive integral representations like this for solutions of certain linear, ordinary, or partial differential equations. But for now, let's just take it for granted that J0 can be written this way. If you want, you could even think of it as a definition of J0. So that's an example of where you might have an integral. And another would be if you're taking a course in probability or studying the flow of heat in one dimension, or maybe diffusion in one dimension, you would run into an object called the error function, often abbreviated ERF. There it is. So the error function, it's an integral involving this Gaussian, bell-shaped distribution, e to the minus t squared. So if you're integrating from 0 to x under e to the minus t squared, then basically you get the error function with this normalization constant out in front. Notice that x is playing a little bit different role here. X is an upper limit of integration in this case, whereas here x was a parameter inside the integrand. So these are the kinds of ways that we'll see x appearing in these integral representations. And we'll often be interested in what happens for either very small or very large x. Another special function defined, or that can be represented as an integral, is the so-called gamma function, written with this capital Greek gamma, defined by this integral. This interesting object was invented by Euler, or maybe discovered, depending on your philosophical point of view about these things. But what's so interesting about the gamma function is that it's a nice generalization of the ordinary factorial function for integers. So like if you plug in a positive integer n, gamma of n will be just ordinary n minus 1 factorial, it turns out. But what's so cool about the gamma function is you can now interpolate between the integers and compute things like gamma of 1/2 or 3/2 to give yourself a concept of what would it mean to take 1/2 factorial or something like that. Gamma obeys the sorts of properties you'd expect of a factorial-like object. For instance, this multiplicative property that x times gamma of x gives you gamma at x plus 1. behaves sort of, it obeys some of the same algebra that the factorial would obey. All right, so those are examples of some functions that have nice integrals representations. And here, like with the gamma function, in the next lecture, or maybe it'll be 2 lectures from now, we'll see how to represent gamma of x asymptotically for very large x, which will give us a cool formula for an asymptotic approximation to n factorial, something called the Stirling approximation. You may have run into it in courses in statistical physics or probability. And so here we can derive the Stirling approximation with our methods, including higher order corrections to the usual Stirling formula. Okay, so that's all just stuff that's coming ahead. And other special functions, Airy functions, the exponential integral we saw in the first lecture, these also can be written as integrals. So the other point, though, about why we might care about integrals is that often when we're solving linear ordinary differential equations or partial differential equations, we will use methods of transforms. Like we might take the Laplace transform of the equation or the Fourier transform, and then we can derive an equation for the transformed solution. And then to get back to the actual solution we want, we have to take the inverse transform. And so what that does is it expresses a solution to a differential equation as an integral. These inverse transforms always take the form of some kind of integral. Now, frequently we cannot do the integral in closed form. We can't do it exactly, but we can estimate it for either very large time or very large distance, the far field approximation. And those kinds of approximations will be important in many different scientific and engineering settings. So that's, my apology or my justification for why we would care about doing integrals. But, you might just take the point of view, hey, I like integrals. I like calculus. I want to know how to do some integrals approximately, even if I can't do them exactly. So let me pause there and see if you want to weigh in with your own favorite reasons for why we would do integrals, or you maybe have some questions about something I said so far. Is there any point to bring up, either in the chat or verbally? Okay, well, so let's continue then. So the example I want to focus on for much of the lecture today is this beast, an integral defined as a function of a parameter x that sort of looks a little bit like the error function, in that we're integrating something that's bell-shaped. I mean, if we were to draw the graph of the integrand, e to the minus t to the fourth, let's see. So that would be, it's not that different from e to the minus t squared. We're only interested here in positive values of x. So it sort of looks, very flat, and then it comes down. I'm drawing here the, sketching the function e to the minus t to the fourth as a function of t. And you could think of this as a question about what's the area under this curve to the right of some place x. Right, so we're sort of trying to figure out what is this area under here. And so that defines our function of x, I of x. And we'll be interested in it both for x going to 0 and x going to infinity. All right, so let's see. This, by the way, is a problem that is discussed in Bender and Orszag. So if you want to see their treatment of it, that would be, that's going to be Bender and Orszag, starting around page 251, continuing for several pages. So I don't know, maybe up to around 254 or so. Okay, so let's start with small x, because that'd be like if we wanted just the total area under that curve almost. Okay, now one naive thought would be, well, if I'm thinking about small x, maybe I should expand that exponential. So if we were to use the Maclaurin series expansion for e to the minus t to the fourth, that is e to the minus t to the fourth is 1 minus t to the fourth plus t to the eighth over 2 factorial, right? Because I'm just reminding you that something like e to the u is 1 plus u squared over 2 factorial plus u cubed over 3 factorial, et cetera. So we could keep going like this. And that is a convergent series. So for those who worship at the altar of convergence, you would think, well, that seems pretty good. Why don't I just integrate term by term? You could do that. If we use this immediately, watch what will happen. Then what would we get? So we're interested in going from x to infinity. So 1 minus t to the fourth plus t to the eighth over 2 factorial minus ... dt. I mean, maybe you can already see there's going to be trouble in thinking about that because, I mean, even the first, just integrating the 1 from x out to infinity, looks like that's giving something divergent. And similarly, all of the separate terms are going to give you divergent integrals. So that doesn't, but they're going to cancel out and apparently to give you something finite, but it's just too mysterious to look at that. So you get this and you have too many divergent integrals if you look at it term by term. So that is not the recommended method. Instead, what might make more sense if you just sort of think about the question is to split the problem into 2 integrals. I mean, if you look at the picture, so, you know, we have something like this. If we're interested in what happens, say, for a small x, the area to the right of that x looks almost like the area under the whole curve. And so it's sort of natural to then compute this kind of by a negative space argument, that look at the area under the whole curve. Maybe I should try this in different colors. So like I could take the area under the whole curve and then subtract off this part. That should be nice and small. Right, and then what's left over is going to be that yellow region. So that's a better way of doing this. So instead, let's split the problem into 2. That is, we'll write I of x is the integral from 0 to infinity e to the minus t to the fourth dt minus the integral from 0 to x of e to the minus t to the fourth dt. The beauty of doing that being that the first integral we can evaluate exactly, and the second integral we can make use of the fact that x is small, and there our Taylor approximation for e to the minus t squared will work very nicely. So let me do each of these integrals separately. First, I'm going to show that this one is equal to 1/4 gamma function of 1/4, which is just some nice number around 0.9. Turns out to be 9064 ... So I'll do that. And then we'll deal with the second integral momentarily. All right, so let's first deal with this e to the minus t to the fourth dt. When you see something like this with an exponential, even though it's unfamiliar, you should be thinking gamma function because the gamma function has an exponential in its definition. And so here, the natural move is to just let some new variable tau equal the exponent t to the fourth. So I'll just remind you back here, if I go back and look at my definition of the gamma function, you see that it had e to the minus some argument, e to the minus t. So we're going to make a tau play the role of that t. All right, so I let tau equal t to the fourth, and then that means that t is going to be tau to the 1/4. So taking dt, get 1/4 tau to the minus 3/4 d tau, just taking differential of both sides. And so now I can replace everything in the integral above. This first one that we've been focusing on. So 0 to infinity, e to the minus t to the fourth dt becomes, well, the limits of integration are still 0 to infinity in terms of tau, but now it will be e to the minus tau. The dt is 1/4 tau to the minus 3/4 d tau. And if you look back at the definition of the gamma function, this is just 1/4 gamma of 1/4. You get the 1/4 in the exponent because when you're dealing with the gamma function, you add 1 to this exponent to figure out the argument of the gamma. You can see that by looking back here in this definition. Notice it has an x minus 1 in there when you're looking at gamma's argument being x. So they differ by 1. You go up by 1 from here to get that. So that's what we did. And so it's 1/4 gamma 1/4, which you can ask Mathematica to evaluate, and it's that number I just said. Okay, so that's our first integral. That's the total area under the curve. And then the next thing is to go back and deal with this second integral. This one. And so here we're just going to use the fact that e to the minus t to the fourth can be written as 1 minus t to the fourth plus t to the 8th over 2 factorial, etc. And here we can comfortably integrate term by term. So maybe I'll do that down here. So integral 0 to x, e to the minus t to the fourth dt is term by term 0 to x, 1 minus t to the fourth plus t to the 8th over 2 dt. And that gives x minus x to the 5th over 5. The t to the 8th integrates to t to the 9th over 9. So that gives me a factor of 9 times 2 or 18 in the denominator. So I have plus t to the, no, that becomes an x when I substitute. I'm skipping a step. X to the 9th over 18 minus ... Okay, so now we're almost done. I mean, we can then say that for small x, go back to black. So for small x, we're getting that I of x is 1/4 gamma 1/4 minus the thing I just calculated, x minus x to the 5th over 5 plus x to the 9th over 18, etc. And actually, if you're paying close attention, you might be thinking, why am I saying for small x? I mean, this was a convergent series that I used here. And, oh, actually, maybe I better be careful about my signs. I think I want to write this like that. Yeah. So, I mean, this in fact should work for all x. It's only that if I want to take a very few terms in the series, then I better be doing this for small x. In other words, once x gets fairly large, like say x equals 10, I mean, think about this actually. If you were to substitute x equals 10 into this, how many terms would you have to take to get decent convergence? Look at how crazy this is. You'd be getting, you'd have this little number here, which we calculated is like on, this number is on the order of, what did I say, around 0.9. So I have something like order 1, then minus 10. And then here, now I'm suddenly adding something that's 10 to the 5th power. That's like 100,000. And then I'm subtracting 1 billion. You see how insane this is. This is a terrible way to calculate I at 10, because you would have to take an enormous number of terms in order to get the factorials in the denominator built up enough that you could get decent convergence. So this is a super slowly converging series, and it's terrible for making good approximations. So convergent but useless. Useless in the sense that it's too slowly converging. For any x that is sort of, you know, like substantially greater than 1. I'll show you that later. We'll make some numerical comparisons between our asymptotic results and our convergent results and exact results. And so this is, again, me bashing convergence as something that is overrated in a lot of contexts. Yeah. So is there any question about this part of the argument?
For x larger than maybe just 1, can you still use the Taylor approximation? Like, isn't that argument wrong to begin with, and that's why it's converging so slowly, or is it even converging?
No, this is actually a convergent expansion for all x. I think we could prove that this does converge for all x because we've got factorials in the denominator that I haven't been writing. You know, like, so with this e, if I were to write this out properly, you know, like, what is this term right here? This one is t to the 4th squared over 2 factorial. And our general term is going to be something like t to the 4th to the n over n factorial. And then I'm integrating that. Okay. And so if you were to check the resulting series with the ratio test or whatever, you would find it's a convergent series for any x.
Makes sense.
Yeah, I mean, because the factorial, although it starts out fairly slowly, it will eventually pick up steam. But you have to wait a long time for it to be any good. And that's what's so interesting about asymptotics, is that they work very well with very few terms, whereas convergence sometimes takes an inordinate number of terms before it starts to really be useful. So yes, any other question? Okay, now let's compare this to, I mean, I don't want to completely undersell this series. This series works fine for small x, say less than 1. but anything that's too much larger than 1, it's going to be terrible. So like I say, try n equals 10 yourself if you want to see, or x equals 10. Just to see how slow it really is. Okay, but now let's instead, really what I want to focus on today is the case of large x. All right, so how can we deal with that problem? We're still interested in the integral. From x to infinity, e to the minus t to the 4th dt. But now we're thinking of x much greater than 1. And so the interesting trick that I want to show you is one of the classic tricks in analysis, integrating by parts. This doesn't look immediately like an obvious candidate for integration by parts, because in first year calculus, usually you think of doing problems with integration by parts on problems that have an integrand with 2 functions multiplying each other. Like if I had e to the minus t to the 4th times sine of t or something like that, that would look natural for integration by parts. But how can I do that here if I only have the 1 function in the integrand? Well, here's a nice little trick. The dt can give us what we want. We're going to try to write the dt. Well, let me put it this way. Write the integrand, including the dt part, using the differential of e to the minus t to the 4th. So if I were to expand e to the minus t to the 4th, I mean, using this differential, then I would get e to the minus t to the 4th times a chain rule term from differentiating the exponent, d of minus t to the 4th, which is e to the minus t to the 4th minus 4t cubed dt. So this looks like the integrand, except it's got this extra factor here. So let me pull that to the other side. Okay, in other words, I'm just using the identity that minus 1/4 t cubed in the denominator, d of e to the minus t to the 4th is equal to e to the minus t to the 4th dt. And so I'm going to replace my integrand with this expression on the left-hand side. And that will set me up to do integration by parts, where I'm going to think of this in the way that I always remember integration by parts as u dv. This is my u, and this is my dv. So it's fun. It's a way of making an integration by parts problem out of one that didn't look like it had any in it. All right, so let's carry on with that then. What's going to happen if we do this? We have that our I of x is, using this cunning trick, 1/4t cubed with a negative sign, d of e to the minus t to the 4th. And so remembering that integral of u dv is by parts, uv minus integral of v du. Let me write the uv term. So that's -1 over 4t cubed. V, of course, the v in this problem is just e to the minus t to the fourth. So there's my uv term. And then I have to, it's a boundary term, right? So I'm supposed to evaluate it at the endpoints. And then I'm supposed to go minus integral of v du. So let's calculate each of those. So the uv term, well, when we evaluate at infinity, e to the minus infinity to the fourth power, so to speak, is much, I mean, that's super small, transcendentally small. Plus we have the infinity cubed in the denominator. So we're not getting any contribution from infinity, that's for sure. And so we're just left with a term 1 over 4x cubed e to the minus x to the fourth. So that's the boundary term. And then I have, so putting in the v du, let's see here. So what are those giving me? I'm a little bit confused about something here. I'm seeing a factor of 3 that I'm being boggled by. Oh, I see. God, now I understand it. Right. V is my e to the minus t to the fourth. But I have to go back and look here at this expression for u. Right. So if u is -1/4 t to the -3, then du is going to give me 3/4 t to the -4. dt. I think I did that right, except I seem to be off by, yeah, no, that's good. Does that look reasonable? Yeah. So what we have here is a remainder term. That is, I'm going to claim that this should be thought of as 1 over 4x cubed e to the minus x to the fourth plus, let me call it r of x, where r of x, the remainder, is -3/4 integral from x to infinity 1 over t to the fourth e to the minus t to the fourth dt. All right, so we've just written our I of x in terms of this, what we hope is the main contribution, this term, plus a term that we hope is asymptotically smaller. And that's, if integration by parts is working, this is what we've accomplished. That we have now generated a very tiny remainder. And actually, we have good reason to expect that this remainder term is much less than I of x. And also that r of x is much less than this term we just generated. So let's see if we can understand why that's true. If you stare at the expression, maybe you can tell me, why is it reasonable? Actually, let me try something different. Usually I ask you and then someone says something out loud, and it tends to be the same person every time. So can I have you type in the chat, why is it reasonable intuitively to expect that R of X is going to be much less than the term we just generated? So I'm going to look at the chat and see what you have to say. All right, I see some nice responses popping up here. So yeah, let's see. So remarks are being made that because X is large, says Mark, the factor of 1 over t to the fourth. I mean, you're focusing here, Mark, on this, right? Sort of compare this to what we had in the first place when we were generating we were looking at I of X. This stuff right here is the integrand for I of X, but then this has this additional term, 1 over t to the fourth, where the t is greater than X, which is itself a large number. So we're getting a boost. We're getting an extra 1 over X to the fourth kind of thing happening in the integrand. Right, and this is similar to what Jackson is saying too. Yeah. So this is the idea that this 1 over t to the fourth in the integrand is really is going to help us out. So because of the extra 1 over t to the fourth in the integrand, and the facts that on this region of integration, t is greater than X, and the X we're assuming is much greater than 1. So we would expect this, and now let's just verify it by doing a careful calculation. Actually, I think that was good that we did that thing with the chat, because I noticed some of you are just kind of floating and not particularly engaged. So I might do this from time to time just to, check in with you. Okay, so good. All right, so in fact, what we're going to be able to show is that, given that this remainder is much smaller than this first term, what we have generated here qualifies as an asymptotic approximation to the integral I. So we're going to prove that. So what I'm claiming is that, in fact, we're on the brink of showing here that I of X is truly asymptotic to this first term, 1 over 4x cubed e to the minus x to the fourth. Well, let me say it this way. So to prove this, well, we have to show, let's estimate the size of the remainder. We want to show that the remainder is much less than the first term, the term that we retained. Okay, and so to show that, well, let's estimate the size of the remainder. I see I have a little note to myself here. I want to compare my asymptotics to the exact results in Mathematica. So I will do that momentarily, but I think I might need another page of notability here. So I'm going to add a page. Okay. All right, let's get started on this calculation though. So R of X in magnitude is 3/4, and magnitude of integral from x to infinity, 1 over t to the 4th, e to the minus t to the 4th dt. Now, at this point, we're left with the problem that we don't know how to evaluate this integral either, right? I mean, this integral is even harder than the one we began with, the integral for I of x. So we don't expect to do this integral exactly, but we don't need to. We're only trying to do an estimate. So we need an upper bound on the integral. And here's a clever way to do it. I mean, there are various ways, but one way that's kind of slick is we could use our integration by parts trick again. We could say that this is equal to, this is another use of the trick from earlier, 3/4 integral from x to infinity, 1 over t to the 4th, and then do the trick where we expand that e to the minus t to the 4th dt as 1 over 4t cubed d of e to the minus t to the 4th. So here I'm using the trick again from earlier. And what's nice about this, I mean, this is all exact, but what's nice is that if we notice that we're in the regime where t is greater than or equal to x, we can then write the inequality that this is strictly less than 3 over, so I have 2 factors of 4 in the denominator, that makes a 16. And I can replace those t to the 7th power in the denominator by x to the 7th and take it outside the integral. Where I'm going from t equals x up to t equals infinity. And the reason that's legitimate is I'm just using the fact here that I'm using the fact that x to the 7th is less than t to the 7th. On this domain of integration from x out to infinity. So this refers to my t interval of integration. T is in this interval here. So, so that's it. I've replaced the denominator by something that is, I mean, what am I trying to say? This denominator here is strictly larger than that. So this gives me an upper bound if I use the x to the 7th. And the reason that that's nice to do is that then I get this strict result on the size of the remainder term. Actually, let me just drag this out of my way here. Go down there, just go away, thank you. Okay, and so this I can calculate, this integral now. Hence, the magnitude of the remainder is less than 3 over 16 x to the 7th e to the minus t to the fourth evaluated between x and infinity in magnitude. So this gives me 3 over 16 x to the seventh e to the minus x to the fourth. So there's an upper bound on the remainder, and this is a very tiny term. I mean, that term compared to the term that was the leading term, right? We were saying this is the leading term here. Let me circle this. The leading term has this prefactor of 1 over x cubed. This remainder term has a 1 over x to the seventh. They both have the same exponential term. So this is way smaller, the remainder. And so that is enough to prove what we needed to prove. Let me see, I see a comment or question in the chat. Would it work to compute the limit directly using L'Hopital's rule to eliminate the integral? Let's see, Andrew, are you saying you want to compare the integral to the integral meaning the remainder term expressed as an integral, and you're going to take the derivative of that and compare it to the derivative of the leading term? Is that the idea?
Yeah, the limit. The limit is x goes to infinity of r of x over I of x.
That would
or
work, I think.
To I of x.
Yes, that's a nice idea. You could do. I think that would work. Sure. Yeah, you could do the limit that way. That seems like a nice idea. Yep, you could. The advantage of doing it this way is that if with a little more work, we could keep getting more and more terms in the asymptotic expansion. In fact, this thing that I've just computed will be the next term in the expansion. But yeah, your method will work too. Yeah, right. And Jackson says the relative error can be estimated using these kinds of arguments. Good. So I think now is the place where I can actually compare these different approximations to the exact results. So let's look at what the small x calculation does and what does the large x do. So for this, I'm going to jump out of using notability for a minute. Let me stop sharing this screen. Okay. And I'll share a different screen. So let's share my desktop. Okay. Keep the chat off to the side here. So yeah, I did a little Mathematica calculation of this morning. See if this is visible to you. That's in the way now. Okay, is that all pretty visible for you? Yeah, clear enough. Okay, good. So, okay, I'm going to walk through it slowly. I'll post this on our Canvas page so you could read it later if you want. But the gist of it is, here's the actual e to the minus t to the fourth. It has that bell shape I mentioned. It's flatter on the top than the usual Gaussian, and it decays very quickly and gets very near zero once x gets to be larger than about 1.5. And so we're calculating the area under this curve to the right of some moving point at x. Okay, now, just for curiosity, I asked Mathematica to calculate I of x exactly to see if it can do it. And it turns out it can. I didn't know that this was possible. The answer is given in terms of a special function that I've never studied called the incomplete gamma function. So Mathematica says if you integrate e to the minus t to the fourth with respect to t from x to infinity, where we got to tell it we're thinking of x as a real number greater than 0. Otherwise, it thinks we might be thinking of a complex number for x. Anyway, it then says it's 1/4 gamma function, but it writes gamma with 2 arguments. So I'm not used to this. I think of the gamma function as having 1 argument, just the ordinary gamma function. But apparently there's this object, the incomplete gamma function, that takes 2 arguments. And you can read about it in Mathematica if you want. So anyway, it says it's 1/4 gamma of 1/4 x to the fourth, comma x to the fourth. I ask it to plot that, and it says the exact I of x looks like this. So the area under the curve grows as a function of x. I mean, remember, it's the area to the right of x. So when x is 0, that would be the total area under the curve. That's this 0.9 number that I mentioned. But then as we start pushing x out to the right, we get less and less area. It's decreasing linearly. By the way, notice it sort of makes sense that it's decreasing linearly. That's because as I move x to the right, I'm losing a rectangle of width x to the extent that this top is flat. Right. So you'd sort of expect it to be linear because this top is kind of flat, but then at some point it's going to be not quite linear because this starts to curve. So anyway, we get this linear behavior, then there's some curving, and it looks like I of x is very close to 0 once x is greater than about 1.5 or something. Okay, now we could try to approximate the I two ways. As I say, we could just do it with a Taylor series. So here to do that in Mathematica, I ask it just do series expansion of the exact result with respect to x around the point 0. Give me, say, up to the 5th order term, and it gives me the terms that we calculated ourselves with Taylor series. And if you compare that to the exact I of x, you see that it works decently. The orange curve matches the blue curve pretty well for x moderately small, considerably less than 1. You know, this has the wrong qualitative behavior once x gets too large, but if we include more terms, we can eventually get this. But okay, so if you only want to take one term, it's not very good, even at x equals 1. On the other hand, if we look for a larger x, well, Mathematica knows how to do that too. You would ask it to do series expansion of the exact answer. But now you say expand around infinity. That's its way of doing the large x approximation. I asked it to do out to the 7th term, and it gave me this funny expression I wasn't expecting, e to the minus x to the 4th, but then it writes plus big O of 1 over x to the 8th, which I don't really even know how to think about that. It looks weird, but that's what it did. And I suppose it's right in some sense. I haven't really made sense of it though. And then it's giving me these terms, which are actually the first 2 terms in the asymptotic expansion, those are terms we calculated. But now here's kind of the money comparison, which is, let's just look at what happens if we only take one term in the asymptotic expansion and compare it to the exact result. Look at how good the asymptotics, which is this orange curve, look how well it matches the blue curve once we get greater than 1. And remember, this is supposed to be true out at x going to infinity, but we're not taking x very large. Now, maybe you can't see much because both curves are very close to 0. So what I ask it to do is do a logarithmic plot where you can see much better what's happening. Here are numbers like 100, 10 to the 5th, and so on, small numbers like 10 to the minus 4, 10 to the minus 7. You can see that the orange and blue curves are really hugging quite closely once x is larger than 1. So it's really working even down to minute values of the function, you know, and for significant size values of x. It's not too great for small x, but we wouldn't expect it to be. All right, so that's one way of comparing. Is there any question about anything about the Mathematica? Let's see what's happening in the chat. So Jackson says Mathematica has a new feature in 12.1 called asymptotic. No kidding, I didn't know that, which behaves somewhat differently than just series. Oh, interesting. Okay. Oh, thank you, Jackson. I'll try using that from now on. I mean, we could try it right now, should we? I think I have a new version. This is not actually real live Mathematica. This is just a PDF, but I can open up the real thing. I'm curious what will happen. Okay, this is dangerous because there's no telling what will happen. Let's try it. So I'm going to go, let's see. I think this notebook is alive. I don't know if it is. I guess it is. So what should I do? Let me try typing in asymptotic, hey, look at that. Asymptotic of, and I'll type in this expression. I have no idea what this is. It's my first time ever using it. Asymptotic, how do I use it? Let me learn something by looking at the information. Asymptotic. Oh, I just say x goes to x0. All right. So fine, let's say x goes to infinity. Let's see what it does. Oh, come on, that's not what I want.
The second way of calling it is like series, where you can give the number of terms. And I don't know if it's going to spit out just the same thing or not.
What do you mean? I'm supposed to say asymptotic series?
So see how in the help menu there were like two different function calls? The second
Yes.
form looks
Oh,
like,
I see. I could ask it to give me two terms. Like this. Wait, did I need to put some brackets on there? Yeah, x, x0, and there we go. So let's do it like this. Oh, I see. X expanded around infinity, give me two terms. Like that. Let's try that. You're teasing me.
Sorry, I should say I didn't try this out myself. I'm on 12.0. So.
There we go. That gave me something. So let me ask it to give me 7 terms. Or let's say, let me ask it to give 9. Because it's a computer, why not? Boom.
That's interesting. It gave you the same one that we came up with, I think.
It does, right? So you can see what it's doing. This was our leading term, right? I don't know if that's visible. This is the e to the minus x to the 4th times 1 over 4x cubed. That's what we calculated. And then there's negative 3/16 e to the minus x to the 4th over x to the 7th. That's our correction term. So that's cool. I had no idea that I could do that, but I like it. Thank you. Excellent. That's great. Very, very good.
I think
Okay,
it's
I'm going
only
to save
a couple
that.
months old.
What's that?
I think this feature is only a couple months old.
Is it really only a couple months old? Okay, nice. All right. So let me leave that then. I also wanted to make the comparison, point out the way that Bender and Orszag do the comparison, which I found interesting too. So let me jump back into sharing my Notability iPad here. Yeah, so this is now taken from the book. It's interesting. The way they do it is they say, suppose you graph the approximation, either using the Taylor series or the asymptotic expansion. Compare the approximation, but normalize it to the exact I of x. So take the ratio between them. So to the extent that you're getting 1, you're getting a really good approximation. And so here they're showing, okay, they look at an 11-term Taylor series of the approximation over I of x. That's this curve. So notice it's very close to 1 for small x. It's doing great. But after all, you're taking 11 terms. And then as soon as you get a little bit larger than 1, it starts getting terrible. Or if you take 10 terms, it's pretty good. But again, it rapidly gets terrible once x gets substantially greater than 1. Compare that to what you see if you only take 1 term in the asymptotic series divided by I of x. Here, you're getting pretty close to 1 once you're greater than about 2, but you've only taken 1 term. And it's even doing pretty, here's with 2 terms. This one is 2 terms. I mean, you can see this is doing decently even with just 2 terms. On the other hand, for small x, it's not doing great. So between using Taylor series for small x and asymptotics for large x, you can actually do pretty well, except in this one little sort of difficult region. So anyway, it's interesting, like to understand the qualitative behavior, these techniques give you a lot of insight. All right, so I think I'm ready to leave that example now. And let me move on. So I'd just like to finish by talking about integration by parts as a more general technique that gets used in asymptotics. So where it's especially interesting to use integration by parts, where it comes up a lot, is when you have integrals of the form that are known as Laplace integrals. So integrals that have an e to the x times a function, like we're seeing here, if I have e to the x times some function of t. And you can also have another function of t multiplying it. And these limits can be, arbitrary a to b, it could be 0 to infinity, whatever. But we're thinking about a large x limit of such an integral. So when you have something like this, it's really set up for integration by parts. This is discussed in Bender and Orszag on page 258, but let me summarize the main point, which is, let's try our tricks again with integration by parts. So the move that we would think of doing is to write this as an integral from a to b, and the strategy is do whatever it takes to make this be e to the phi of t inside a differential. Right? I mean, that was the kind of move we did last time. We wrote differential of e to the minus t to the fourth. So we're going to do that here on this e to the x phi of t. Now, if we take that differential, it's going to generate itself times a factor, a chain rule factor of x phi prime of t dt. So let me put that in a denominator over here. There's my x phi prime of t, that chain rule term, and then the f of t can sit above it. And so this is all correct at this point. I just have to remember that I'm referring here to t equals a and t equals b. Okay, so that's looking good. And now, by the way, you can immediately see that there's something a little bit dicey about this move, which is we have to assume, in order to get away with this, we're assuming that phi prime of t is not equal to 0 anywhere in this interval of integration. So let's assume that for now, and then later we'll see what we can do if that's not the case. But we're going to assume that. So if that's correct, then we can use integration by parts on this to say that this is 1 over x. So here we do by parts, thinking of this as the u, and this is the dv. So I have to go uv, so it's 1 over x, f of t over phi prime of t, e to the x phi of t, all of that between, evaluated at the boundary t equals a, t equals b, and then minus what we hope is a smaller term, 1 over x, oops, excuse me, 1 over x, integral from a to b, d by dt of f over phi prime. All right, that's going to be my du. And then I have the e to the x phi of t dt. And so the caveat here is that we're hoping, if this exists, we don't even know if this integral exists, but if this integral exists and is asymptotically smaller than the first term, then we have a nice natural asymptotic approximation coming from our integration by parts maneuver, which is that we would get that the whole thing we're trying to calculate, I of x, will be asymptotic just to this first term, 1 over x. Well, let me write it this way. Put a big bracket. F of b, so evaluated at these boundary points, e to the x phi b over phi prime of b minus f of a, e to the x phi of a, phi prime of a. That would be our asymptotic approximation under the assumptions I just mentioned above. So now usually one of these two terms will dominate. You won't typically have both. So you can often get away with just one of those two. Will dominate as x goes to infinity. By the way, we're also assuming here that these are not just zero in disguise. So we're assuming that f of b and f of a are not both zero. Right, because you see those factors f of a and f of b sitting here and here. So if both of those are zero, then this term isn't even present, and we need to think harder. So I'll just mention like what you expect when you have this integration by parts situation, which is that the method, as you can see, is generating powers of 1 over x times other stuff. Right, like if you look back here, I've got this 1 over x behavior times something else that depends on x here and here. But as far as the powers, you're getting 1 over x, an integer power of x. So I guess I should emphasize that. It means generating integer powers of x. And so this method will fail for certain problems. I mean, if that's not actually the correct x behavior, it will fail on problems where the correct asymptotics involve, let's say, fractional powers of x, x to the half, that type of thing, or terms that involve natural logarithm of x. I mean, this method will not be able to generate such terms. And as I said before, it will also fail sorry. It will also fail if we have the derivative of phi being 0 in the interior somewhere. So if that equals 0 somewhere on t less than a less than b, then, or, I mean, there's one other way it can fail, which is notice that we had this term right here. this ddt of f over phi prime. If that thing blows up somewhere, that might be a big term, right? That not going to be asymptotically smaller necessarily in that case. So that's another possible failure mode of the method. It can get into trouble if ddt of f over phi prime of t goes to infinity in the interval AB somewhere. In which case the new integral blows up. So I'm mentioning all this because integration by parts is great when it works, but it often doesn't work. And so we're going to see next time some of the remedies, for how do you get asymptotics when integration by parts doesn't work. And so that's what stationary phase will do for us, and steepest descent and saddle points.